Okay, so we've been looking in section 6.3 at different properties that we can use to gauge how good of an estimate an estimator is, or maybe if I've got two different estimators, how can I determine which one is more efficient than the other. And so we've been thinking about bias, and we've been thinking about variability. And one more property I want to take a look at combines these two, and that's called the mean square error. That's abbreviated with MSE. And so as the name applies, what we are going to do is take the mean, the average of the squared errors. In other words, the distance of our estimator from the value of the parameter it's trying to estimate. So by definition, the mean square error of theta hat would be the expected value of theta hat minus theta squared. And similar to how we work, we prove the property with variance. There's a proposition in the book 6.3.3 that shows we can rearrange terms, basically doing some algebra, that the mean square error we can write as the sum of the variance of the estimator plus the bias squared of that estimator. So this is a good way of comparing both the variance that we looked at with efficiency and this notion of bias. So this is a good way of measuring, maybe I have an unbiased estimator that has a lot of variance that might not be very desirable, compared to having an estimator that has bias, but it's not very big and it doesn't have a lot of variability. That might be a desirable quality to have in an estimator. So just a couple of things to point out here, again, is that this is a criterion that weighs both of the two previous properties that we looked at, bias and variance. And if we have two unbiased estimators, this is not going to contradict anything that we looked at in the previous example, in the sense that if we have two unbiased estimators, the estimator which has a smaller MSE is also going to be the one which is more efficient, because if this is if this is equal to 0, then the smaller value of this is going to lead to the smaller mean square error. And so in general, we're oftentimes faced with this trade-off between variability and bias. And it's not always the case that unbiased is better. And sometimes we've got two unbiased estimators and we need to decide which one might be better. So let's take a look at an example on the next slide. Okay, so in this video, we're going to take a look at a random variable x, which has a binomial distribution where we know how many trials we have. There are n trials. What we don't know is what's the probability of a success in each of those trials. So we've got one parameter here, which is p. And one estimate that we've already taken a look at is if I, let's say, estimator 1 be the sample proportion. So I would take the number of successes and divide by the number of trials. And this is unbiased. We can calculate the expected value of this, and we can show that what we get when we take the expected value of x over n is what we get back as p. So that's an unbiased estimator. We've also looked at the variance of this, which would basically be like the standard error of a sampling distribution squared. So the variance for the distribution of sample proportions is p times 1 minus p over n. And since this is an unbiased estimate, the mean square error would be the variance, which is this, plus the bias, which is 0. So in this case, the mean square error and the variance are equal to each other when we have an unbiased estimator. So that's an estimate that makes sense. Another estimate for the proportion we'll see in a bit, but in some cases we can think about, well, what happens if we assume there were two more trials? So that's where the 2 down here comes from. So instead of n trials, we're now going to take two more trials. And I'm going to assume that one of them was a success and one of them was a failure. So I'm going to add one of them to my success total on top. So before we had x over n, now I'm adding two trials. One of them is a success. And let's consider this estimator over here. And so the first thing that we can observe is that this is an estimator which is biased. If I were to calculate the expected value of p hat 2, our second one, then what we would get is on top we would get the expected value of x. And since we're dealing with a binomial distribution, the expected value of x would be n plus p, or n times p. So if I were to calculate the expected value of this, I would get n plus p plus 1 all divided by n plus 2. And so that's over here. And so if I were to calculate the bias of this estimator, I would take its expected value minus the parameter that we're trying to estimate. And so if we simplify this difference, the bias of this second estimator is 1 minus 2p over n plus 2. And one thing to observe here, like the variance example that we looked at a few slides ago, as n gets really large, the bias of this estimator also goes to 0 because our denominator is getting really large. So although this is a biased estimator, for large values of n, the bias gets smaller and smaller. So asymptotically, this bias is 0, which is a good property to have. So there is some bias, but the larger that n is, the smaller that bias gets. So this is also a reasonable estimator to use. So let's compare properties of this estimator, namely, let's look at its mean square error and compare it to the mean square error of our first estimator, which was maybe the more obvious one using the sample proportion. Okay, so in this video, we're going to now take a look at the variance and then the mean square error for this second estimator for the population proportion. This p hat 2 was the one where we said, let's assume we have two more trials. One of them was a success, one of them was a failure. And we showed in the previous slide that this was a biased estimator, although as n goes to infinity, that bias is going to head to 0. So it has some bias compared to the sample proportion, but that bias actually heads to 0 as n goes to infinity. And so let's go ahead and calculate the variance and mean square error for this second estimator for the population proportion. So the variance, excuse me, would be, remember that this is equal to x plus 1 over n plus 2. We added two attempts. One of them was a success. So we can pull out this 1 over n plus 2 from inside the variance, but we need to square it when we pull it out. And so we get 1 over n plus 2 squared times the variance of x plus 1. And since x is a binomial distribution, then we have 1 over n plus 2 squared. The variance of x for a binomial distribution is n times p times 1 minus p. And we have that shortcut for binomial distribution. And then we add to that the variance of 1, and that's a constant, so it has no variance. So altogether, the variance of this second estimator would be n times p times 1 minus p all over n plus 2 squared. And to calculate the mean square error of this estimator, we can now use the fact that it's going to equal the variance of this estimator that we just calculated, plus the bias of the estimator, which we calculated in the previous video, and we're going to square that bias. So for the variance of this second estimator, we above have n times p times 1 minus p over n plus 2 squared. And the bias we also calculated as 1 minus 2p over n plus 2. So that was on the previous slide. So we're going to take all of that and square it. So if we add those two fractions together, this gives us a mean square error of n times p times 1 minus p plus 1 minus 2p squared, all divided by n plus 2 squared. And we want to compare that to the mean square error for the first estimator, which was the sample proportion p hat. So we called this p hat 1. So that's probably the more obvious estimate that you would use. And in that case, the bias of that estimator was 0. So the mean square estimate of that would equal the variance of that estimator, which is p times 1 minus p over n. So we've got these two variances, these two mean square errors. It's really complicated to compare them by looking at these formulas. So we can plot the two of them on the same set of axes. So what we're looking at here in the graph in blue, this is corresponding to estimator P1, which is using the usual sample proportion. And in red, this dashed graph in red, what I'm plotting is the mean square error for this second estimator, which we got by saying, let's add 2 trials to our sample, and let's assume one of them was a success. And so in red, this is the mean square error for this one. So you can see these are both functions of p. And I should say, in this case, I plotted this fixing a value of n equals to 16. So even if we have a relatively small sample, this estimator p hat 2, when n is small, is going to have some bias in it. But what we see from the graph is that actually the mean square error is smaller. As long as when p is really, really small, so when p is close to 0, it's not going to be a good estimator. When p is close to 1, it's not going to be a very good estimator. But for all of the values in between, actually the mean square error of this second estimator is less than the mean square error of the sample proportion. So we'll see in some cases it might be more preferable to use this p hat 2, x plus 1 over n plus 2, as an estimate for p because its mean square error is less for most values of p, and its bias is actually not very big for large values of n. So that makes this actually a pretty nice estimator for the population proportion.